So in here you have a positive charge, and as you know from the previous video, the electric field lines go outwards from the positive charge. So if you have a small positive, we can call it a test charge, it will be repelled by this. So the question is, what is the force being applied on this small positive charge? The reason why we use a small positive charge is we don't want to overwhelm the electric field produced by this. So the formula for working out the force on this positive charge is Q. So that is the charge of this positive particle, so it's measured in coulombs, times by electric field strength, which is given by E. Now let's look at a negative charge, and now you still have the small positive charge because always use a small positive charge, but the field lines are going in. So this small positive charge will be attracted towards the negative charge. So now we can use our analogy to gravitational field. So you can think of this as Earth, and you have a small mass. So remember that we are on Earth and we have a small mass, so we don't affect the Earth that much. It is so small that we ignore it for everything that we do. So that's the same reasoning goes for the small positive charge. Even though this positive charge will have its own electric field, it is small compared to the electric field of the charge. So it's pretty much negligible. It's just like our mass is pretty much negligible when we are looking at gravitational field from the Earth. Okay, in this slide we're going to look at gravitational and electric field. So up here I have drawn the electric field lines. So they're coming towards the surface because the surface has negative charge. And here we have the surface of the Earth, and I have the gravitational field lines going down. So in both cases, I'm making these lines equal distance apart, so you can assume that the field is constant in both of the scenarios. So in electric field, a charge will experience a force, and there will be a small positive charge, so it will experience a force downwards. And in gravitational field, there's a mass, and the mass will experience a force downwards. So if I move this mass up, so if I gain height, I'm actually gaining gravitational potential energy. So higher I go, higher the gravitational potential energy. So I can do the same thing for a charge. So if I move against the field, I will actually gain electrical potential energy. And when I released a mass from a certain height, that mass changes into kinetic energy in the gravitational field. So same thing happens to the charge. If I move the charge against the electric field, it will gain electrical potential energy, and that potential energy will convert it to kinetic energy. E.g., there is work done on the charge. So same for gravitational field, there will be work done on the mass. Okay, so in here I put them in a table. So in gravitational field you have forces equal to mg. So in electric field you got forces equal to EQ. So Q is equivalent to mass, and E is equivalent to A. So gravitational potential energy is mgh, electric potential energy is EQD. So d is the distance moved against the field. And as the mass falls down, that gravitational potential energy is converted to kinetic energy. So in here, you got the electric potential energy converted to kinetic energy. So work done is force times distance. So force is EQ. So that's the force experienced in an electric field. And D is the distance moved. So the work done by that charged particle will be EQD. So this is similar to work done is equal to mgh in gravitational field. Okay, now I want to work out what is the work done per charge or per unit charge. So I'm going to divide both sides by Q. So this Q and this Q will cancel out. So now we end up with ED. So now we can define work done divided by charge as voltage. So now I've introduced another new concept. So voltage is work done per unit charge. So electric field strength can be defined as voltage divided by distance. So the unit will be volts per meter. So there's two formulas for defining electric field. So there's two formulas for working out the electric field strength. So it's volt divided by distance and force divided by charge. And the units are volts per meter for this one and newtons per coulomb. So they both are equivalent. So if you want to think about the gravitational field equivalent, if you rearrange force is equal to mass times acceleration, you get acceleration is equal to force divided by m. So force is measured in newtons, m is in kilograms. So it will be newtons per kilogram. So notice that it's very similar to this unit where you have newtons per coulomb. In here we got newtons per kilogram. So our mass is the one that is experiencing the force. In here our charge Q is experiencing the force.